All right. We're going to talk about taking averages now, and I think everybody knows how to take an average. Another word to describe average would be the arithmetic mean. The mean of something. Okay? If I want to find the mean, and there's lots of symbols and things if you're in a math textbook to make it look real confusing, let me zip my book over here. See, we got all these Greek letters and strange symbols, and it makes it sound really difficult. It's really not. Okay, all we're going to do, if we want to, here's a good medical example. Bada boom, bada bing. Find the mean of each set of quantities. Pulse rates. What's that? I didn't even plan on it. I just looked up. We've got medical stuff here. My wife is a nurse, by the way, so I kind of, sort of, I don't know anything, but I pretend like I do. Okay, here we go. Pulse rates of 68, 84, 76, 72, and 80. Taken at whatever interval, time interval in between. We don't have to worry about that. We just want to know the average, okay? And everybody's taking averages. I know you have. What do? You add them all up, and then you figure out how many there are, and then you divide by that number. So I'm going to turn that into a big old fraction and divide by 5. Okay, now if I add these up, get your calculator out, punch the numbers, we're going to get 380 divided by 5, and that's going to give us 76. Okay, so the average of those pulse rates is going to be 76. You take all the numbers, you add them together, and you divide by however many numbers there were to begin with, and that's the average. Okay? Pretty straightforward. All right. The only time where it might be like a gotcha kind of question is, let's say somebody gave you these numbers. 21. Here's your list of numbers: 21, 62, 0, 17, and 40. And you need to find the average. You can't neglect that 0. Okay. Pardon me as I reach for a calculator because I just pulled this one out of the air. I'm not looking at a book. So what do? You add them all up, 21 plus 62. It might be tempting to drop the 0 is not contributing, leave him out. You can't. Because we need to count that 1, 2, 3, 4, 5. We need to count that as one of our 5 numbers. Otherwise we're going to get it wrong. Okay, so even though it's a 0, we can't neglect it. So 21 plus 62, okay, plus 0. We know it's not contributing there, but we're still going to divide by 5, not divide by 4. So that's going to be 140 divided by 5. And that's going to be 28. Okay, so I just, again, pulled those numbers out of nowhere. All right, sweet. Okay, so that is taking averages. So let's talk about fractions, shall we? Like I said, I normally teach algebra and beginning algebra. And I have little sayings I put on the board to torment my students. The first of which goes without saying, but I'm going to say it anyway. Math is fun. Every day I write that in the top right-hand corner of the board so they can stare at it the whole class. And then as we progress through material, depending on what we're talking about, I throw extra sayings in there. Well, guess what the second one is? Fractions rule. Okay? Sometimes I sneak a baby in there. Fractions rule, baby. Okay? They do. They really do. So let's talk fractions. All right. Come on now. Go on, right? All right. Let's talk fractions. A fraction is part of a whole. Okay? It's part of a whole. The easiest way to visualize fractions, and for some reason people don't, shy away from them, don't like them, and all that stuff. The easiest way to visualize a fraction is with the old pie chart. If I draw a 4-piece pie here, and I'm interested in one of those pieces, I say I'm interested in the fraction of 1 over 4. Okay, so 4 is the number of pieces in the pie, and 1 is the piece that I'm interested in. Okay. Pretend I'm drawing, nice and pretty. Here, I've got 2 out of 4 pieces shaded. Okay, now you may say, well, that's half the pie, right? we're going to get there. 2 out of 4 is 1 out of 2, is half. Okay, we'll talk about that. Okay, fair enough. Here I'm going to have 3 out of 4 shaded. Okay, sounds pretty good. Here, I'm going to have 4 out of 4 shaded. And you may say, well, isn't that just one whole pie? Why are you calling it 4 out of 4? Just call it 1 whole pie. And of course, if I take 4 and divide it by 4, remember fractions are just division problems. 1 divided by 4, 2 divided by 4, 3 divided by 4. If I take 4 divided by 4, I get 1 whole pie. 1. Okay? Now, it's possible to have more than 1 whole pie. You know, if I have this situation, now I've got 5 pieces. Okay, I still look at a single pie, and the pieces have to have the same number of pieces in each pie. But I still just look at that single pie and say, there's 4 total possible pieces, but I've got 5 out of 4 pieces. Okay, and we call that an improper fraction, which we can write as what's called a mixed number. Okay, so this is called improper. Okay, these are all called proper fractions. Okay, improper fractions can be written as what's called a mixed number. Okay, a whole number part, you can see it. I've got 1 whole pie and I've got 1/4 more, so I could call that 1 and 1/4. 1 whole pie and 1/4 more. Okay, now it's easy to see it with the pie charts staring us in the face, but if we just had the number 5/4, it's not quite as easy to understand how that's 1 and 1/4. So what we do is we go back to old longhand division here. And we say, let's take 5 divided by 4. Okay, let's do it. 4 goes into 5 one time. 1 times 4 is 4. I subtract, and I get this little remainder of 1. So way back in the day, we said we had 1, remainder 1. Well, what that remainder is, it's the fraction of 1, remainder 1, divided by 4, your number out front here. So this is my whole number 1, and then I got a fraction of 1/4. And that's how we do that. Okay, so if I had, 8/3, let's say, longhand division, 8 divided by 3, 3 goes into 8 twice, 3 times 2 is 6, I subtract and get a 2. I was hoping for one where I didn't have matching numbers top and bottom like I did there, but I screwed myself again. This 2 up top, that's the whole number, and then the fraction here, the remainder, is 2/3 fraction. Oops, 2/3. Alright, so that's how I turn an improper into a mixed number. If I want to go back the other way, we take the denominator times the whole number, and then we add the numerator to it. So watch what we do here. 4 times 1 is still a 4, plus 1 more is 5, and then I keep the denominator, 5/4. 3 times 2 is 6, plus 2 more is 8, and I keep the denominator. Okay, so that's how we return a mixed number back into an improper. Alright, so far so good. Alright, there's this little annoying requirement that goes along with fractions, and that's that we always want to reduce them to what's called lowest terms. Okay, and we did that up here. 2 out of 4 is half, right? Half the pie. Well, think of how many different ways you can express half. 5 out of 10 is half. 50 out of 100 is half. 5 million out of 10 million is half, right? All of those, we know those to be half in terms of our everyday experience, but how do we turn those numbers into a 1/2 when we have something else, like a 2/4 or something else? Well, in order to do that, we need to talk a little bit about factoring. Let's talk about factoring. Okay, factoring is when we take a smaller number and we break it up into a larger number, and we break it up into the product of smaller numbers. Okay, so it takes a big number, and big is of course a relative term, like a 6. I can break a 6 up and call it a 3 times a 2. Right? 3 times 2 is 6. Those are factors of 6. Okay, now technically I can take a 6 and I can break it up into 6 times 1, and I still call those factors, even though it's the same 6. 6 times 1 would be factors of 6. 3 times 2 would be 2 different factors of 6. Okay? I like to use this little factor tree diagram just for plain old factoring, but you'll see in a minute I'm going to write it slightly different. How about if I factor 40? There's different ways to start. You may say 20 times 2, you may say 10 times 4. Doesn't matter how you start, you're going to get to the same answer. You keep going. Now you got to factor the 10. 10 is 5 times 2, and 4 is 2 times 2. Okay, so if we kind of consolidate at the bottom, if I take it 5 times 2 times 2 times 2, and by the way, this dot means multiplication in algebra. We try not to use the old classic time sign in algebra because we don't want to confuse it with the variable x. Okay, so a dot is one of the ways we express multiplication. I make my variable x's, by the way, like a cursive x. I know we'll get to that eventually, but if I take 5 times 2 is 10, times 2 is 20, times 2, I'll get that same 40. So if you were asked to factor 40, you know, writing it like that would be good. Or you could get really slick, and we haven't talked exponents yet, but this is really 2 times 2 times 2. That's really 2 to the third power. So you could write that as 5 times 2 to the third power. Now that's being really cool. Okay? But that's straight up factoring. Take some big number, break it up into the product of smaller numbers. Okay, and we use that idea to reduce fractions. Let me just go to that same 2 over 4. Well, 2 you say is what we call prime. A prime number can't be factored other than to call it itself times 1. So I'm just going to do that. I'm going to call it itself times 1. Again, I'm writing it a little differently now, not the tree arrangement. 4 I'm going to factor as 2 times 2. Okay? Now, once I have it in this form, if I have any common factors, in other words, the top and bottom of my fraction have matches, I can just cancel those matches right out of there. And what's left? 1 over 2, 1/2. Hey, we got it, we're done. So 2/4 reduced into 1/2. Okay? How about this one? How about 25 over 30? Well, we say 5 times 5 is 25. We say 5 times 6 is 30. We got a matching pair of 5s we cancel out of there. And we call it 5/6. All right? Reduced to fraction. Okay, word of caution now. First of all, when I'm doing this little cancel, what am I really doing? I'm really saying 5 divided by 5 is 1, right? So I'm really taking 1 times whatever is left over, and we know 1 times whatever is just the same whatever, right? Times 1 doesn't change anything. So they don't disappear, they don't turn into zeros, they divide into the value of 1, okay? But we just say they cancel. Now we can only do that little cancel technique when these are multiplications, when these are factors. If I give you something that looks very similar, 5 plus 5 over 5 plus 6, okay, no way can I just do what I just did there. No. No. Can only cancel like that when I've got nice multiplications top and bottom, not additions or subtractions. Okay, can't do it. All right. Sweet. All right. So reducing fractions, we're going to factor top and bottom. If you have your own little factor strategy, reducing strategy, by the way, you know, 35 over 60, let's say. You may say, well, I don't do this factor technique. I just think of something and I divide it through on the top and the bottom. Right? Maybe you say that. Like, I know I can divide a 5 up there, and 35, and some people even kind of mentally, okay, cross that off, divide by 5, 35 divided by 5 is 7, 60 divided by 5 is 12, and just kind of do one little maneuver like that, 7, 12. I'm okay with that, and again, I'm not going to be grading you on anything, but if you've got the little mental kind of cancel in your mind, that's fine, okay? But what you were really doing is what I did. I just like to show it. You were really saying 7 times 5 is 35, 12 times 5 is 60, goodbye 5s, 7/12 left over. Okay, that's what you were doing. And that's fine if you have this kind of mental way to do it. Okay, sweet. All right, what about adding, subtracting, multiplying, and dividing fractions? Multiplying and dividing is actually easier. So let's do that. Let's multiply fractions. Okay, adding and subtracting is a little more complicated. If I show it generically, and that always makes it look harder, some fraction a over c times some, or a over b, pardon me, times some fraction c over d, okay? I multiply the numerator, so it's a times c up top, and I multiply the denominator, so it's b times d on the bottom. Okay? Incidentally, in algebra now, when letters are side by side like that, it means multiplication, even without a times sign snuck in there. Okay? We don't need to put a sign. That means a times c, and that means b times d. Okay? So if we put kind of a practical problem out there, 3 over 8, again, that dot means times 5 over 11. I'm going to multiply right across the top and get a 15. I'm going to multiply right across the bottom and get an 88. But then I need to stop and say, okay, reduce this fraction if needed. Okay? So we would have to do a little homework and say, can I reduce that fraction or not? Okay? This often helps us know whether or not we can do it. If you look here, if there's anything that might cancel here, and nothing does, right? I mean, an 8, I could call that 8 4 times 2 if I factored it, right? But 11 is prime, 5 is prime, 3 is prime. Actually, I can call the 8 2 times 2 times 2. If I go all the way to primes, there's nothing going to cancel there. Okay, and sometimes it's not obvious, and we got to go over here and think about it a little bit. Okay, but it's always a good practice, and generally required in a math class anyway, that you reduce those fractions. Okay, so just multiplying is not good enough. We need to reduce afterwards. All right, let's look at this example. 3 over 7 times 2 over 5. Again, straight across the top, 3 times 2 is 6. Straight across the bottom, 7 times 5 is 35. And just like that, we're done. Okay, no reducing necessary. What about a whole number times a fraction? What about 5 times 7 over 12? Uh-oh. That's a new one. Well, remember, fractions rule. In fact, if I write it again. And we'll sneak the baby in there. Fractions rule, baby. I can take any number, slap a denominator of 1 under it, and make it a fraction. Now it's easy. 35 over 12. Can I reduce? No, there's no 5 or 7 hidden inside my 12. I can't reduce. The best I could do is turn it into a mixed number, right? And what the heck? Let's do that. 12 goes into 35 twice. That'll give me a 24. And what will I have left over when I do that? I have 11 left over, right? So it's going to be 2 and 11 over 12. All right, sweet. How about C? 2 over 9, 2 over 3 times 9 over 4. Okay, 2 over 3 times 9 over 4. Well, when I multiply it out, I get 18 over 12. And this one, I can reduce. Okay? Because I know, for example, there's a 6 hidden inside my 18. 6 times 3 is 18. 6 times 2 is 12. Cancel those 6's out of there. Okay, 3 halves is all that's left. Yeah, I could call it a mixed number, but 3 halves is reduced. Okay? All good there? Incidentally, when the numbers are small like this, it's not so bad. But if the numbers were bigger, let's say that was 20 over, 35 times 9 over, even 40, whatever. 40. Boy, I'm going to get a big number on the top and a big number on the bottom, and it's going to take some time to reduce all that. Even if we made that a 90, that's even more terrible. Well, I always say in that case, don't multiply them. Just write it like this. Okay, nothing reduces yet, but I'm on my way. I'm starting this factor process. Now I gotta see if there's anything hidden here and there. You know, I know there's a 5 inside my 20. I know there's a 5 inside my 35. So maybe I would call 24 times 5. 90. I'll call 9 times 10. I'm going to work my way at it here. 7 times 5 is 35. 4 times 10 is 40. And you see right there, I can kill off some 5s and kill off some 10s right there. And 4s. Woo! I didn't even see that. Now I saw it. I'm done. 9 over 7. Okay? Just like that. Had I actually multiplied them, I would have 2 colossal numbers to deal with. And then I'd have to start breaking those colossal numbers apart and factoring and canceling. You know, that's not the end of the world, but this way is easy. I've already got factors. They're nothing canceled directly, but I'm already on my way if I don't physically multiply them. Just write them like that if the numbers get big. Okay? Yeah, the time. Let me just quickly do, if you have mixed numbers, okay, 3 2/3. Now I'm going to open up parentheses here. Another way to show multiplication in algebra is like that. If you need to multiply mixed numbers, there's really no shortcutty way to do it. Just turn them back to improper fractions. 3 times 3 is 9 plus 2, 11/3. Okay, now I'll switch to the dot. Times 5 over 4. Okay, here I would look for canceling opportunities. There's not one, right? Nothing's going to cancel, so I could just go ahead and multiply it right on out here. 55 over 12, which again should be a perfectly acceptable answer, but since it was given to us as a mixed number, we might want to take it all the way home and turn it back into a mixed number. So we know 12 goes into 55 4 times. That's a 48. And I'll have a remainder of 7, so it's going to be 4 and 7/12. Okay, that's it. I will pick up on division of fractions here in a moment.